Okay, let me give you a moment to copy this example down. Okay, and then we'll talk about the example. Okay. So we want to use integral tables to help us evaluate this definite integral here. The integral from 2 to 3 of the 1 over the denominator x squared times square root of 4x squared minus 7 dx. Okay, now when you look at this, okay, remember you have learned some good integration techniques, and this actual integral, we would need to use a technique called trig substitution to work it out. The book, but we're going to focus here on using tables of integrals. So what's happened is over, well, calculus is, let's see, since Isaac Newton, it's, many hundreds of years old, right? Isaac Newton lived back in the 1600s, right? So over the years, scientists have encountered integrals, and sometimes they were successful in doing the integration. What I'm trying to say is not all integrals can be, you can't find antiderivatives for all integrals, but there are many integrals that you can find antiderivatives of, and as as scientists have discovered antiderivatives for integrals, they write them down, and eventually a book or a table of integrals was created. Now there are actual books that have of integrals, but our textbook has tables of integrals that are it's about 120 like integral formulas. And for section 5.8 only, you can use these table of integrals to help you. They're located in the appendix of your textbook. But let me show you where they are in Blackboard, okay? So let me see here. I want to, yeah, let me go to, hold on here. I want to go to Blackboard. Okay, and I'm going to go to, okay, well, first of all, is the Blackboard visible to everybody? I like to make sure. Okay, good. Thank you. Okay, so if you go to course content, course content is basically, well, what that is it's, as we do our lessons, and the lessons are recorded, I put the recordings in the course content. Our first chapter is chapter 5, integrals. Here's naturally a little introduction to that chapter. And to see the course content, we click the Here button. Click here. And now you have, for each section we've covered, you have the lectures, the recordings. Now, of course, I update these after every class, I update them. Well, obviously, we have to add a recording here to section 5.7 because we just did a new lesson, right? A new lesson. But we're interested in section 5.8. So section 5.8, the table of integrals, what I've done is I have made that available to you right here. So all you need to do is click on table of integrals, the link, and I'd like everybody to do this. Click on the table of integrals, okay, and up comes the table. Okay, so if you click on the link, now let me show you the table that you should be getting. Let me do that right now. Let me see, where is it? One moment, class. Let me find the table. Let me bring it up here. You should be able to download the table from at that link. I'd like everybody to try it, and let me bring the table in here. Sorry, let me find it. Give me a thumbs up, by the way, if you're able to successfully download that table. Sophie's done it, wonderful. Jacob has, Audra, Leping, Samuel, excellent. Nicole, Gloria, Abadar. All right, so and you will have you'll need this for section 5.8. So here's the table. A lot of formulas. So the basic formulas are right in the beginning here, right? Give me a thumbs up if you're able to see the formulas okay in the window. Wonderful, excellent. So all of these formulas over many, many years have been developed, have been discovered for antiderivatives, all these antiderivative formulas. Okay, and altogether, there are 120 of these formulas that the Stewart textbook provides. Now, what we want to do, and usually it breaks them into sections depending on the forms, what type of form the integral is. Okay, so if we go back to the problem here, okay, we want to find a formula that's going to help us get the antiderivative. So what I'd like you to do is I'd like you to look through the formulas, okay, and try to find a formula that you think sort of matches the integrand here. The integrand is equal to this integrand here, 1 over, and the denominator is x squared times the square root of 4x squared minus 7. So you have a variable squared, okay, in the bottom here you have a variable squared times the square root of a difference of, well, something that looks like a variable squared minus a constant. So look through the formulas and try to find a match. Try to find a match for a formula, an antiderivative formula that's like a match to this integral here. Okay, so Sophie says 36, and we'll take a tally here, and it's okay to be right, it's okay to be wrong, right? 19, okay, and I'll write these down on paper here. I can tell you Not 19, okay. 36. Okay, so 36, one moment here.
Actually, the second number isn't squared, so I'm not sure if 36 would work either.
All right, well, 45 is being suggested as well. And Sophie, you're right to question 36. You're right, your instincts are correct on that, because in 36, the a squared stands for a number. So you have a number minus a variable squared. But in the square root here, you have a variable squared first minus a number. So it looks like formula 45 is going to be the right match. So that's good, everybody. Good. Formula 45 will work. But formula 45 here, if I just make a note of formula 45, okay, if I hold on here, one moment. One moment, class.
So
okay.
What did you say A and U represented again?
Well, in the, let's see, for formula, let's write that formula down. I'll write it right here. Formula 45. So you have the integral of 1 over u squared times the square root of u squared minus a squared du. Okay, that equals the square root of u squared minus a squared, all divided by a squared u plus a constant. So you see here in the formula, you're integrating with respect to u. So u is your variable. Anything else is a constant. So that's why a is a constant. So in the square root, you have a variable squared minus some constant squared. Here, well, you have, well, 4x squared is what is that squared? 4x squared is equal to what squared?
2x.
2x.
2x squared. Right. And 7 is equal to what squared?
Square root 7.
That's right. So we have hope that maybe, well, I mean, how am I going to utilize formula 45?
You factor out a 4 from the 4x squared minus 7. Can you factor out a 4? And then, because that's a perfect square, take it out of the square root?
You know, Maria, I hadn't even thought about that. I think that is a definite possibility.
Because you could take, you would factor out the 4, so you'd end up with 4 times x squared minus, what, 7/4?
You'd have this, let's see, 4x squared minus 7 is equal to the square root of 4 times, well, it's a little, hold on here. Let me get my, one moment. Okay, so yeah, we could write this as the square root of 4 times x squared minus 7/4. And then we have the square root of 4 times the square root of x squared minus 7/4. Yeah, that would work.
And then you
And then-
can take that out, and that goes on the left side of the integral.
Yeah, you could do that. You could do that. That would work, actually. That would work. Might we have another thing we could do? Being that we have a 2x squared here and we have a u squared here. So Maria, that's a good suggestion you made. Let me offer another suggestion too. We have 2x quantity squared here in our problem, and then we have a u squared here in our problem. I mean, in our formula. What could we let u equal? You know, to get this for this formula here, this formula to work.
U equal to x.
You could let u equals 2x. Good. That's right, Leping. That's right, Samuel. Let u equals 2x. And what's a equal to, by the way? A equals
Square root of 7.
Root 7.
square root of 7. Right. So it's usually easier. The substitution approach is more general. And for many of the problems here in section 5.8, substitution is really what's going to do the job for you. So let's go to the solution here. We have an idea what to do. So we've already feel that we can apply formula 45. And I'm going to let u equal 2x and try a substitution here. So let me let you copy down to this part here. Okay, right where I put the check there. And then we'll talk a little bit. Okay, let me give you a moment to copy this page down. Okay, so if u equals 2x, then of course u divided by 2 will equal x. All right, and so we're formula 45. This is a formula that somebody discovered probably several hundred years ago, maybe more, and it's been cataloged. So mathematicians can use that formula without having to, you know, if they have an integral where that formula can be utilized, they can use it, and they don't have to derive the formula. Okay, which is nice. Right. So, okay, u equals 2x. That means u over 2 equals x. And so now I make the substitution here. Are there any questions up to this point? Notice the limits change. If u equals 2x, the x limit of 3 becomes a 6, and the x limit of 2 becomes a 4. So the u limits change because we are making a substitution. Now u over 2 quantity squared, by the way, that's u squared over 4, right? So of course, we have to, I mean, we want to try to make the, we want to apply the formula. And so there's like some nuisance stuff here, right? Like the 1/2, you know, that's kind of a nuisance. That isn't in this formula up here. The 1/2, that can be just brought out front, right, of the integral. And then this here is u squared over 4. So the 4 can be also brought out in front. All right, and if I may, I'll go to the next page to continue this. Are there any questions so far?
So for me, real quickly, so I understand that we had 4x as the u, and then
Or 2x's to u?
yeah, 2x, yeah, that's what I meant. And then so I guess I want to know, like, how would we get u over 2 for the x squared times the square root at the bottom? And
Okay.
Mhm.
Well, if u equals 2x, and which we, you know, that's our substitution, and we divide both sides by 2, u over 2 has to equal x.
Oh,
And
right, you just plug that in for x, right? Okay.
That's right. That's right.
All right, thank you.
Sure, you're welcome. All right, well then we move forward here, and you know, so this is, I just recopied what we had on the last page, and now u over 2 quantity squared is the same as 1/4 times u squared. And the 1, so, and think of the 1 over a fourth. 1 over a fourth is the same as 4. Okay, so 1 divided by a fourth is equal to 4. And so we pull that out of the integral. And now we are good to go. We're applying formula 45. So what I do is above the equal sign, you know, now, you know, when I apply formula 45 to get the antiderivative, above this equal sign here, I put a 45 with a circle on it to say, hey, I'm using formula 45 from the table of integrals. And then I just work it out. Just work it out, and we get our answer. Please let me know if you have any questions. And just a reminder, these table of integrals are only to be used for section 5.8 questions. Okay, so like in your homework now, you know, don't use these formulas for the other sections. On your exam next week, you know, you'll know which questions are from section 5.7, 5.6, 5.5, 5.8. You'll know. Because the questions that are from section 5.8 will say use table of integrals, okay? And so if the question doesn't say use table of integrals, then you can't use the table of integrals to help you, okay? Are there any questions at all? Okay, well then finally then, this is our answer. What is it? To sort of write the final answer, I mean, WebAssign would accept this answer, but I'm going to distribute the 2/7 to both of those terms there. And if I do so, I will get that the integral is 2 root 29 over 42 minus 6/28, and then that reduces to this. Okay. I'd like to do one more problem with you, and then I'm going to have you work a little bit on, do some practice with these section 5.8 problems. But are there any questions before we move on? All right.
I have a question.
Oh, yes, Todd.
This is regarding the week of the exam, though, not specifically these.
Oh, okay. Okay.
So are we still? I assume not, but are we still just gonna have a homework due for the week of that we're supposed to be doing the exam?
There will have to be some homework due. Just because it's a summer class, I mean, it's a summer class, so even though, you know, you're still, you know, maybe like you have to do part 2 of the exam, say, still, but you could have a homework assignment due, yeah. But remember, you can take late extensions. But yeah, just because the way the course is, just because we're doing it in 2 months, you know, I understand what you're saying. It would be nice if you didn't have any homework to worry about during your exam period, your exam window. I'm going to look into that a little bit, but there will have to be something due during your exam window. It's just because of the time limitations of the course, Tal. But I'll make a note to study that a little bit. That's a good question, Tal. So on Thursday, I will address that as well. Thank you for that. Good question. All right, I'm very glad I'm glad I actually had a discussion with you on these a little bit about the exam, because then you ask good questions, and then you know, that helps me. All right, well now here we have another interesting problem here. We want to use integral tables to help us evaluate that integral. Okay. So this is a very, you know, probably the original person who, you know, found a formula to help with this problem probably used like integration by parts or something of that nature. But at any rate, we have some tables to help us. So I want you to look through those tables, table of integrals, and try to find something that will help us here. Obviously, the formula has to have an arctangent in it, right? Now, an arctangent is the same in terms of notation. That's the same as this notation, right? So, all right, so let me give you a little time here, and when you think you've found a formula, chat it out, and we'll make a list. Okay, we got formulas 95, 90 from the table of integrals. Okay, 95, all right. And I got my table in front of me. Okay. I'm looking at 2. Let's see here. Well, okay, you're very close. Formula 95, you're very close. But so let's focus there, okay? Okay, Nathan thinks Formula 92. And Formula 92 is going to be your class. Good job, Nathan. The rest of you, you were very close. So let me ask you, before we, I mean, sometimes you have to think about, you look at the, okay, what substitution do I need to make here in order to use one of these formulas? So what do you think a substitution should be? What substitution might work here?
E raised to the 15x.
That's right. Good, Nathan. E raised to the 15x power. So we're going to make that substitution, and I'll show you why Formula 92 is going to work. Okay. All right, let's go to the solution. Now, I say right in the beginning, Formula 92 most closely resembles this integral, but actually you don't kind of know that yet, okay? I just sort of say it so I can write the formula here, okay? Maybe I won't even say this. Maybe this comment I'll cross out because, but let me write Formula 92 down here. And here's the substitution, u equals e to the 15x. That means then that du dx is 15 times e to the 15x. And so du then is 15 times e to the 15x dx. Okay. We're utilizing the chain rule here. And okay, so look what I do then for the integral. And sometimes you kind of have to, I have this e to the 30x here, right? But e to the 30, e to the 30x, interestingly enough, can be written as e to the 15x times e to the 15x, because when the base is the same, you add the exponents. So if you take e to the 15x times e to the 15x, that gives you e to the 30x, right? So, and vice versa. Well, I have what I need to rewrite this integral in terms of u. I have what I need. Isn't that amazing? So it turns out that when I do the substitution, u equals e to the 15x power, the integral becomes the integral of u times the arctangent of u du. And that's Formula 92. And that's why Formula 92 works. Please let me know if you have any questions. So many of these problems in section 5.8 are ones where you have to rewrite the integral. You know, you have to think about what substitution you're going to do. You might have to rewrite the integral first a little bit. It can vary. It can vary. But all right. May I go to the next page where I write down the final thing, final comment? Nicola's good. All right. Very good. Tall's good. Wonderful. Shaji. Okay. Wonderful. Sean. Good. All right. Let's go to the next page then. Thank you, Leping. Very good. So just then, final statement. There's your antiderivative. So you see these table of integrals save engineers a lot of time. And of course, now with things like MATLAB, there are professional programs that can do integration. But we are focused here on using the tables because they will, they're just a nice way to help you do these problems. It reinforces substitution. It reinforces your integral knowledge. You know, in your 200 level courses, you'll learn how to use MATLAB a little bit. But all right, are there any questions before I stop the recording? Okay, I'll stop the recording.